Welcome, everyone. My name is Peter Corliss, Technical Marketing Manager at ScyllaDB. I'll be your moderator for today's webinar, Sharding All the Way Down, a closer look at Scylla's shard per core architecture. Scylla is a big, fast, NoSQL distributed database, perfect for highly available, highly performant terabyte scale workloads. Next slide. I also want to let you know about P99Conf, a free online conference centered on high-performance, low-latency distributed systems. ScyllaDB is sponsoring the event, so I've been busy reviewing the submissions and interviewing speakers from across the industry. It's going to be great. If you like today's webinar, you are going to love P99Conf, so make sure you register for it at p99conf.io. Next slide. Without further ado, I have the pleasure of introducing to you our speaker today, Avishai Ish Shalom, Developer Advocate for ScyllaDB. Take it away, Avishai.
Thank you very much, Peter. So as Peter said, I'm a Developer Advocate for ScyllaDB. I'm going to say a few words about the company. So ScyllaDB is the company behind the open source database Scylla. It's basically a drop-in replacement for Apache Cassandra. It also has API compatibility not only with Cassandra, but also with Amazon DynamoDB, which means that you can use Scylla with the same drivers, same applications that work with either Cassandra or DynamoDB, basically drop-in replacement. It does have 10 times the throughput of Cassandra with very, very low latency, even on the high percentiles. That's what it says here, low tail latency. Highly recommend that you look at our benchmarks and also, conduct your own, because all benchmarks are lies, basically. We have an open source version, we have an enterprise version, and of course, we have a managed database as a service cloud solution. So Scylla Cloud, head over there if you want to check it out. The company was originally founded by the creators of the KVM hypervisor, which is, if you don't know it, it's the hypervisor that runs all of the modern clouds of today. So let's get started. But before we dive into the details, I want to take a quick look at this model. This is basically a scaling model. It's a mathematical model for how systems scale. So this graph basically details how a system responds in terms of throughput and in terms of the value and performance that you get from it when you add more and more resources and you apply more load into the system. So this model is called the Universal Scalability Law because presumably it applies everywhere. And the idea is that initially when you add resources, you start seeing linear increase in system response. You get more throughput proportional to the amount of resources that you added. But at some point, you start getting diminishing returns. So you add resources, but you get less and less speed up. And the reason for that is because you have usually some kind of shared resource or some kind of contention. So that shared resource would have queuing and contention on it. So this is known as Ando's law. And this is something that's been known for a very long time. And this means that you get sublinear scaling. So you add more and more resources, the system does become faster and you get more throughput, but not as much, okay? So it becomes harder and harder to scale the system. But at some point, you start seeing negative returns. And this is something that a lot of people kind of ignore or don't acknowledge or don't know. But there is a point where you start seeing coherency issues. So think about traffic jams, for example. Actually, the throughput of the road is much lower than off-peak hours. So whenever you need to have some kind of strong synchronization or consensus between multiple parts, so think about a group of 5 people that have to reach a unanimous decision. Any one person in the group can make everyone wait. So the more people you add, the worse it becomes, and it actually gets slower and slower and slower. So this is an area of negative returns, and you really don't want to be in that area, because once you get to that area, more resources and more load you apply, actually the system is going to get slower and slower and slower. So this is the basic model, and just keep it in your head. I'm going to circle back to it later on. So let's talk about how the database architecture was traditionally, the database architecture of traditional databases. It's been like this for at least 20, 30 years or so. This is how we build systems, not only databases. So the common architecture is basically a shared memory architecture and goes something like this. So this is in MySQL and Postgres architecture, a lot of our databases as well. So you have clients, and the clients connect using some kind of network protocol, usually TCP, and they connect to a query engine. And you would have a thread or process that handles each client. And those threads or processes would have some responsibilities like parsing the query, SQL in this case, and they would have some buffers, and they would do some data manipulation per client. And they don't access the storage directly. What they do instead is they talk to a bunch of other threads known as the IO threads that are bundled in some thread pool inside the storage engine, InnoDB in the case of MySQL. And those IO threads would talk to the disk. They would read data to the disk. They would manage the disk. Of course, you have a problem with shared access to disk. So they would have locks to synchronize between each other, so they don't, step on each other's toes, and they don't corrupt data and that kind of stuff. So what happens here is you have two thread pools that communicate between each other, and they communicate through shared memory, and they have locks to synchronize with each other. So both the query engine threads would have some kind of lock to coordinate with the storage engine threads, and the storage engine threads would have some kind of lock to coordinate between themselves. And if you have some kind of shared cache, then you would also have another lock, to manage the cache, and so on, so on, so on. So that's the general architecture. And likewise, databases like Cassandra or MongoDB back in the day, they have a similar architecture, but instead of having a storage engine with threads for that storage engine, instead of having thread for client architecture, they have somewhat different architecture, where they have asynchronous threads that deal with multiple clients per thread. So you have an M to N threads per client mapping, but other than that, it's basically the same. And on the storage side, instead of having user space threads that deal with the storage, you have kernel tasks. So basically, kernel threads that deal with the storage, and this is done using a mechanism known as the memory map file, basically. So the idea is that you expose a file to the program using a shared memory interface. So that's like a native construct in POSIX systems. And the interface that you have between the memory mapped file and the user space thread pool is basically a page fault. You access a page in memory, and if the data is not there, then you block, and the kernel goes to disk and brings you the data and puts it in memory, and you continue from there. So a little bit less locks, but actually what you've done is you moved all the locks to the kernel. You still have the locks, you still need to do the synchronization, but now the kernel is in charge of it. But otherwise, it's basically the same. And this is how we've been building databases for a very, very long time now. So just to summarize the architecture, you have a process or thread per client connection, or some kind of non-linear mapping. You have some IO threads or kernel tasks to do to manage the storage, and you have synchronization primitives like mutex or futex to maintain storage consistency and access to all shared resources. This is known as the standard shared memory architecture. So now that we understand how databases are built, let's understand what happened in the last 20 years in terms of hardware evolution. What happened to the hardware since the days that we designed this architecture until today? Okay, so this is a graph of RAM prices and RAM size. So it's basically a log-scaled diagram that shows you what happened to RAM prices per megabyte. And you can see that it's basically an exponential drop. So in the last 20 years, we've seen the prices drop by a factor of like more than 1,000. So it's like a huge drop. And if you think about this, now we're seeing servers with terabytes of RAM. So this has been going on for quite a while. As you can see, this is a graph from the 70s. I actually have data from 57 more or less. But the trend is pretty obvious, and it's probably going to continue for at least a while. This is a graph of what happened in the CPU ecosystem. And this is a little bit more interesting picture. So again, we have a log scale graph. And if you look at the orange bars or the brown bars, this is the number of transistors that we have per CPU. And you can see that we have an exponential growth in the number of the transistors. This is known as Moore's law. You've all heard of it. Basically, it says that the number of transistors is doubled every year and a half, and it's been true for a very long time. But the picture gets a little bit more complicated since about 15 years ago. Okay, so what happened is that you can see that the frequency is basically leveling off. Okay, so the CPUs are not getting any faster in terms of frequency. So we've been around the 2 gigahertz, 3 gigahertz mark for almost like 10 years now. And the reason for that is that if we increase the frequency any more, then first of all, we're going to waste a lot of power. But second problem is that around 5 gigahertz, the silicon starts to melt. So we can't actually run it that fast. And that's a physical problem that we can't override. So single thread performance as a result is starting to decline, meaning that it's not getting any faster. And you can see it on the blue dots. And what we do to work around this is we basically add more and more cores. So we get more polarization, but single cores are not getting any faster. And this is why we start seeing, you know, processors. 15 years ago, we started seeing multi-core processors. Now we have processors with, you know, tens of cores on a single chip. So just to give you an idea of like a summary of what happened in the ecosystem. So the number of cores jumped in the last 20 years from 1 core to servers with 256 cores, sometimes even more. RAM jumped by a factor of 1,000. We used to have servers with 2 gigabytes RAM. Now we have servers with 2 terabytes, 4 terabytes, and even much more than that. Disk space again jump order of magnitude of 1,000, so 3 orders of magnitude again, from gigabytes to terabytes. At the same time, the speed of disk, the seek time, so latency that it takes to get data from disk, so to read, let's say, 1 byte, dropped again by 3 orders of magnitude, from milliseconds to microseconds. Network throughput, so we got an increase by only 2 orders of magnitude, so not as much as the rest, but still a huge improvement, from 1 gigabytes to 1 gigabits per second to 100 gigabits per second. So this year, this is what we're seeing this year. We're getting CPUs that each CPU, so it's not even multiple CPUs, each CPU has 64 cores, and that means 128 parallel threads per CPU. We started seeing NICs deployed in data centers with 400 gigabits per second, NVMe disks with 10 microsecond latency that have 1.45 terabytes per device. So if you think about a server that has, you know, let's say 20 or 24 disks, that's a lot of storage per server. And of course, DDR5 is being deployed this year, and it's going to have 2 terabytes per DIMM. So again, think about how much RAM you can stack into a single server nowadays. The largest server on Amazon currently, and it's been commissioned I think even in 2020 or the beginning of 2021, it has 224 cores. So it has, you can run 448 parallel threads, and it has 24 terabytes of RAM. So just think about this. This means that actually a lot of data sets are no longer considered big data. You can actually put them all in RAM on a single machine. So even the definition of big data, you know, changed significantly in the last 20 years. So this creates a problem because we have a lot more data, but the speed of RAM actually hasn't changed too much. You know, the size is growing to insane degrees, but the latency hasn't changed much in 20 years. And the bandwidth does grow, but it doesn't grow as fast as CPU. So here you have a diagram that details what we call the CPU RAM storage gap. So we have a growing gap between the speed of processors and the speed of memory. So now we have a problem that we can't pipe data to the CPUs fast enough. So they spend a lot of their time stalled waiting for data from memory. And it has become a big problem. And similarly, we have the same problem with disks, because disks are now huge. And yes, they are faster, but in terms of piping data to a CPU, you know, we're still kind of blocked. And actually, NVMe disks are approaching the speed of memory nowadays. So they used to be like slower than memory by a factor of 1 million. Now they're only slower by a factor of 1,000. So it's becoming a huge problem, just piping data to the CPU so it could do its work. And because the bandwidth of RAM is limited, and just to give you an idea of how limited it is, we're talking about bus speeds of 400 megahertz, 800 megahertz compared to 3 gigahertz of modern CPUs. And this is for all the cores together. So you get more and more cores for the same bandwidth of a single bus of the RAM. So you're going to exhaust it. So now a lot of the programs are actually blocked on memory access. So to alleviate the problem, a partial solution was invented, and this is known as the non-uniform memory access architecture. And the idea was that we segment memory into separate parts that are independent of each other, and each CPU would get its own, zone of memory that it manages and it has, secluded access to. And this means that when a CPU accesses its NUMA zone, it has high priority access, which is much faster. But if it tries to access a foreign zone that is managed by a different CPU, then it would have some kind of penalty, and it would actually have to wait. It's going to be slower. Okay, so you have local and foreign zones, and the local zones are faster, and the foreign zones are slow, and this is like why it's non-uniform. And this actually helped a lot, as long as you can make sure that the data sets are intersected, so you don't have any kind of cross access between the data sets. That's basically the condition for under which you get this speed up. And the problem is that a lot of our software was written as, under the shared memory hypothesis, basically. So you can't actually utilize NUMA for that kind of software. So only software that's been specifically designed to utilize NUMA can actually benefit from this. And this also has become a big problem. Some databases support this, some don't. The support, of course, is to a varying degree of success. And similarly for runtimes like Java and Go and so on. So if you remember the Universal Scalability Law from before, this is, from actual benchmarks on MySQL, you can actually see that, how this law applies to reality. So this is from one article that compared the performance of two MySQL versions and how they scale. And you can actually see that 5.6, for example, is already getting into the negative speedup zone, even with about, what was like 30 CPUs, so 30 cores, so more or less like 60 parallel threads, starting to slow down already. It's not even the non-linear speed up region. It's way into the negative region, which is like a big no-no. And 5.7 is a little better, but again, it's already hitting the non-linear region even from around 12 cores or so, and it's approaching the negative speed up region from 40 cores or so. So the end result is that MySQL, and this benchmark, by the way, is ideal conditions. So in reality, actually MySQL maxes out around 48 cores most of the time, even lower. And it doesn't matter if you add more and more cores, it's not going to get any faster. You're going to get contention on memory. You're going to get contention on locks. You're going to get contention on disk. So it doesn't. You can't actually scale it much more than that. And also, you have a lot of context switches. So what is a context switch? A context switch is when you switch tasks either from one thread to another, or let's say from user space to kernel space, you switch between some kind of user task to kernel task. That's known as a context switch. And each context switch has some management overhead that has to be done. And the cost is around 1 to 5 microseconds, which doesn't sound a lot until you remember the relative speed of disk and memory. So if accessing memory is now 10 microseconds, okay, the relative overhead of context switch is now a lot. And if you have a lot of context switches, because maybe you're running a lot of threads on the same CPU, you're basically wasting a lot of CPU and wall time just switching between the threads. So you might be the situation where you waste 10% of your CPU capacity or even more just on transitioning between tasks on that CPU. And this happens because of locks. So if you have a lock and you have to wait for that lock, so you have two options: either to spin on the lock and waste CPU time while you're waiting, or you can do a context switch, which is going to cost you, 5 microseconds, which might be a lot. So if you're going to have a lot of locks, it means a lot of context switches, a lot of wasted time, a lot of wasted cycles. And why do we need those locks? Because shared memory. That's how we deal with shared memory. So as you can see, it's not very efficient. And it makes sense back when you didn't have a lot of threads and you didn't have a lot of calls and the contention was much, much, much lower. So if we want to utilize the hardware that we have today, which is like massively parallel, has a lot of calls, and it's basically, you know, the current, let's say, a limiting factor nowadays is memory bandwidth and disk. This is what we need to do. We need to avoid locks. We need to avoid shared memory because otherwise we're going to have locks. We're going to need to avoid coordination and synchronization as much as possible so we don't go into the nonlinear region of the USL. We want to avoid context switches because it's basically just waste. And of course, we don't want to have any memory copies because it takes time to manage them and to copy, and also we need to synchronize access. So that's basically what we need to do. So.
Great, thanks, Avishai. Hello again, everyone. I just want to take a moment for a quick audience poll. For a sense of scale, we'd like to understand how much data do you have under management in your own transactional database systems? Less than 1 terabyte, 1 to 50 terabytes, 50 to 100 terabytes, or greater than 100 terabytes, maybe even petabyte scale. So pick your answers that best matches your current data set. Thank you. We'll leave the poll up for a bit for you to answer. Also remember to use the Q&A feature you have to ask your questions at any time. We'll answer them all at the end. Now let's get back to Avishai.
So now that we've talked about what happened in the hardware scene, let's talk about the kernel and the architecture of the kernel and all the problems that we have in terms of scaling performance in the kernel. Remember, the kernel architecture is also pretty old, and for good reasons. We can't really, make frequent changes to the kernel. It needs to stay stable, and needs to stay reliable. And that means that we still have a lot of remnants from older days when we had different hardware, and also remember that the kernel still needs to run on old hardware even today. So just to give you an idea of what's going on in the kernel, this is what happens when you get, let's say, a TCP/IP packet. Okay, so initially the packet would get from Ethernet or some fiber optics or whatever to a network interface card. And in the network interface card, you have a buffer and you have some kind of a chip that manages it, and it communicates with the computer using an interrupt, basically a hardware interrupt. So it will raise an interrupt, and then the kernel would handle that interrupt with an interrupt handler, which is a piece of code that handles the driver, basically. And the interrupt handler needs to run on a call. So it can only run on a single call. And what happens is that if you have too many interrupts per second, then that call might be swamped. And this basically limits the throughput. So now that we have a very fast network interface card, like 10 gigabit, 40 gigabits, this actually happens in practice. So the solution that we have is we have cards that have multiple separate buffers and multiple separate interrupts, and usually something like 8. And this is known as multi-queue cards. And each of those interrupts would be handled on a different call. So we can actually scale it, parallelize it somewhat. And the way that we parallelize it is by hashing the packets using the MAC address of the source on the other side, like whoever sent the packet. So the problem with that is that we don't actually know which TCP stream that packet belongs to. We can't actually look inside the packet at that stage because it's still in the Ethernet driver phase. So it might be a different call from the one on which the TCP/IP stack would handle the packet. So it's kind of a problem. So potentially the kernel will need to either invoke the TCP/IP code on the same call where the packet arrived, and then it would have a shared memory problem because you need to put related packets into the same TCP buffer, basically. So either you have to synchronize access between calls, or alternatively, you need to handle the TCP/IP stack part on a different call. So you need to, basically copy to a different call and maybe execute the context switch because something else might be running on that call. So it's going to cost you either way. That's a problem. And then once you're done dealing with the TCP/IP part, meaning you decode the packet and reassemble the stream, whatever it is that you need to do, then you move the data to the application part, to the user space part. And again, you need to do a context switch to move from the kernel space to user space. And again, this might be running on another core because, maybe it's like multi-threaded application. You don't actually control where the threads are going to run. The kernel does its best to have everything core local, but unfortunately, in many cases, it can't. So you're going to have this contention and this overhead in context switches. And also you might have memory copies because you're copying data from kernel buffers to user space buffers. So we do have some technologies, like new technologies like IOUing, which are not being used everywhere, unfortunately, not yet. It's going to take some time, which have zero copy. So in most cases, you are going to execute another memory copy. So all of this is very costly and also very, very limiting in terms of our ability to scale to machines with a lot of cores. And if this is not bad enough, okay, we have other problems. So I mentioned memory locks and context switches, but another problem that we might have is socket locks. If we have a single socket, so most servers out there only listen on a single socket, let's say MySQL listens on 3306, and if you have a lot of clients trying to connect at the same time, you need to handle them, but you might be handling the accept of new clients only on a single call. So there's only a finite rate in which you can accept new connections, and that's kind of limiting. So we have some solutions to this. We can scale accept to some degree, but it's still a problem because we need to synchronize with locks. I mentioned CPU core locality problems, and of course NUMA locality, because if the buffers are shared and you don't know which core you're going to handle them on, this means that you don't have any NUMA locality in the TCP IP stack, and presumably also in your application, which kind of ruins your memory access performance. That's not bad enough. This was just an example of the TCP IP stack, but the same problems basically occur everywhere in the kernel. You have a lot of shared metadata structures and a lot of shared logistics and management structures for counters, for statistics. Of course, the file system, which is global, so you have to deal with the virtual file system metadata and lock access to it, and so on, so on, so on. Same goes for the page cache and other caches that the kernel might have. All of those needs to be synchronized. They have a lot of lock-free structures in the kernel, but still, even if you don't have locks, and often you do have locks, you still have the problems of NUMA and basically memory copies and all those problems. So the kernel tries to be efficient as much as possible, but in reality, it's very complicated and very hard. And we have a real problem of scaling the kernel to machines with a lot of cores. So I mentioned context switches a couple of times, so I want to dive into this a little bit. Whenever you have highly concurrent servers, you're going to have a lot of context switches. And if you're using a thread-based implementation, then if you're going to switch between threads a lot, you're going to have a lot of context switches, because every time you switch between threads on a single CPU, then it's basically a context switch. Every time you switch between user space and kernel space, because maybe you're doing IO, again, it's context switch. And the kernel design basically assumes that context switch is cheap, which was the case 20 years ago. But now, when the relative cost so cheap basically means relative to memory access and relative to disk access. And when the disk access was around the order of magnitudes of milliseconds, this was true. But now that we have NVMe, and NVMe is also getting faster and faster and faster, the relative cost is very expensive. So if we're talking about the disk, it's not even such fast disk, so that has a 20 or 50 microsecond and latency. Let's say it's SSD, not even NVMe. The overhead for single IOPS, let's say that you do a blocking read, then you're going to have a context switch. The overhead is 10%. So 10% overhead on single IO, that's like insane. Okay, so that just to give you an idea of how bad this problem has become and how much worse it's going to be when we get faster and faster disks. So now that we know all the problems that we have in terms of the design of our software and the design of the kernel, the question is, like how do we avoid all of that? How do we redesign our software such that we can avoid those problems and actually scale and use all the hardware that we have? So we need to think about the problem from first principles and basically throw away the old design and start with something that actually takes all of this into account. And what we arrive at is the shard per core architecture that Scylla uses. And the idea behind the architecture is to have nothing shared, so just avoid shared memory completely and avoid locks altogether, and never blocks, so we don't pay the cost of context switches at all, so or at least minimal cost. So how do we do this? In order to avoid sharing things, we need to basically separate the data. And fortunately, Scylla is a distributed database. And in distributed databases, you have this common concept of sharding or partitioning. And the idea is that you take the data that you have, and let's say that each object in the data set has a key. And based on that key, you separate it into non-interacting parts and non-interacting parts. And the way that you do that is you hash the key, the partition key, and then you take that hash, which is basically a number. So hash is a function that kind of an opaque function that translates from an infinite input range to a finite output range. And then you take that number and you take the modulo by the number of non-interacting parts that you want to have. So modulo n, and then you get n non-interacting parts, separate parts, and you just take that number, you put it on a ring, and each section of the ring basically represents like a different shard. Okay, so you can take each of those shards and put it on a different machine or on a different core. You get the idea. And of course, there are problems with this. This is not perfect because we took like an infinite space and then we mapped it into a finite space, and then we broke that finite space into even parts. Okay, remember? So model means we're dividing it into even parts, but that doesn't mean that the access to data is even. So it doesn't necessarily have a uniform access distribution, or not necessarily, the data that we will actually have in the database, it doesn't necessarily have a uniform distribution over the possible input ranges that we might have. So we may see some unbalancing in terms of the distribution of data between shards. It's a problem. It's a fact of life in distributed databases. There's no real way to avoid it. It can be mitigated by some degree by having a lot of small parts, which you can then move between the physical resources. So that's basically what we do. We try to have a lot of partitions and solve the problem this way. So this is basically what we do. We have this problem, but we work around it in a sense. And then we get to this architecture where you have basically multiple layers of sharding. So you have a primary sharding layer, which is sharding between physical machines, servers. And then inside of each server, you have a secondary sharding layer, which is what we call Scylla shards. And that is, each core has its own separate instance of Scylla that's running, that's completely separate from all the other cores. And it's like individual and independent, and you can think of it as kind of like a distributed system inside of a single machine. Okay, so it's basically the same as running on different like small Scylla nodes that just share the disk. Okay, so you can think of the disk as like a SAN or NAS or something like that. Okay, but each core is completely separate from all the others, and it's completely independent. And this is done using a very interesting framework, open source framework called Seastar, which is powering Scylla, but not only Scylla, it's also powering some other interesting projects like Red Panda and Value Store. Red Panda is a Kafka clone written on top of Seastar, and also outperforms Kafka by a lot. You might want to check it out. Value Store is basically a Memcache clone. And again, you can actually see the benchmarks that have been done on the right side. So what you can see on the graph is that you get linear scaling with cores. You can just add more and more cores, and you get linear increase in performance. Of course, at some point it levels off, but like you can scale to tens and hundreds of cores before it starts leveling off. So you get, you finally get this promise of linear scaling by cores. And what is special about Seastar, except the shard protocol architecture, is that it's basically a mini operating system user space. It takes on a lot of the responsibilities that used to belong to the kernel, and it has its own task scheduler to manage concurrency within each CPU and each shard. And it has its own IO scheduler to avoid blocking on IO and basically wasting cycles to context switches. It's fully asynchronous to enable that, and it does concurrency by using user space coroutines. And of course, uses direct IO because if it wouldn't use direct IO, then the kernel will block it, and then you would need to use some kind of multi-threaded architecture, which we want to avoid. Okay. So how does that look like? So the traditional stack, let's say Cassandra, okay, would basically have a thread pool, as we mentioned before, that has shared access to memory, and the TCP stack, and would be managed by the scheduler of the kernel. And then the kernel would decide, which CPU to put which threads on, and so on, so on, so on. Whereas with Scylla, it's a Seastar framework, basically, you have the same number of Scylla instances as the number of calls, and each one of them is pinned to a specific call. It never moves between calls. You never, the kernel scheduler is basically disabled, doesn't do anything. And instead, you have the separate task schedulers of each Scylla call, and that manages the concurrency within the database. So database would have a lot of different tasks that it needs to manage. Let's say compaction or serving clients. Let's say that you have 1,000 clients concurrently accessing the same shard. So you have 1,000 query tasks to manage, plus compaction tasks and fetching from disks and so on. And the task scheduler of Scylla would deal with giving all of those tasks CPU shares, CPU time, and providing IO and all that stuff. And because all the shards are independent and they don't share data between each other, remember, each CPU core is servicing one shard, which also has its own data set, which is separate from all the other shards. So it's very NUMA friendly. Each CPU would only access its part of memory and would never access four NUMA regions. So the traditional stack, because it's all shared memory and you don't actually know which core you're going to run on, it's not NUMA friendly. You're always going to have cross NUMA zones access, whereas in the case of Scylla, you have none of that. Which brings me to talk about the Linux page cache. So the Linux page cache basically is like a giant shared pool of memory. And when you read from disk or when you write to disk, you don't actually access the disk. What you do instead is you ask the kernel to do it for you, and the kernel would copy data from disk to the page cache, to memory. And then you would go to memory and you would get the data from there, okay? But this is kernel space memory that's being managed by the kernel. And what happens when you access this memory page is that the kernel will check to see if it has the data that you asked for. And if you don't have the data, it would block you, basically suspend the thread, and it would initiate a context switch. And you don't have a control over this. So this happens whether you want this to happen or not. And also remember, you don't know in advance whether it's going to happen because you don't know if the data is already in the page cache. So then the kernel would go and fetch the data from disk, and then it would resume your thread by doing another context switch, okay? So you have two problems with this. One is the problem of context switch, and the second problem is that you have an unexpected stop, okay? So it makes the life of a scheduler very, very hard, not to mention, like, even to the point of impossibility, because you can't actually plan what latency you're going to have. So we want to avoid this. This is basically what happens when you're using memory mapped architectures. And it's very, very bad for performance, and actually forces you to use more threads than you would want to. Second problem with this is that you're actually caching twice. So in the case of Cassandra, you have one layer of cache, which is in the kernel of raw data blocks from disk, and second layer of cache, which is applicative cache of decoded data, like in the raw cache and the key cache. Or in the case of MySQL, you would have raw caches and also the InnoDB buffer pool. So you have two layers of cache, and it's very, very wasteful to have same data cached twice. So in the case of Scylla, we actually have a unified cache, which is already decoded, only decoded data. And we don't use the page cache at all. We bypass all of that, which is part of the reason why we call Seastar operating system user space, because it takes on all the responsibilities of dealing with I/O and task scheduling, all that stuff. So we don't use the page cache, and therefore we don't need to hold row blocks in memory. We just copy the data directly from disk into user space buffers, and we decode it, and we only hold in the cache data that's useful and that we know that we need it. And of course, if we're managing the I/O, this means that we cannot ever block, because if we block, then the I/O scheduler of Seastar and also the task schedule of Seastar wouldn't be able to service the other concurrent tasks that it has. So we can't ever block. And how do you avoid blocking when you are accessing disk? Remember, if you're accessing disk, eventually you're going to have to block on something. Okay, so like fully async IO in Linux is not yet a thing, unfortunately. There are some rare cases in which you cannot avoid blocking, especially if you overload the device. So you don't want to do that. You don't want to overload the device. And the problem is that it's very hard to do if the kernel manages access for you. Also, you don't know exactly what the throughput of the device and when you're going to block. And if you basically put too much pressure on the device, so the kernel is going to basically put you in a queue, and you're going to wait on that queue, and then you've lost control and you can't do anything. So what we do is that first time you install Scilla and you start it up, it runs a benchmark on your disk, and it automatically finds the capacity and the bandwidth of the disk and the latency of the disk, and it auto-tunes itself to have a concurrency just below the threshold over which you would block. Okay, so we have an auto-tuned I/O scheduler that knows the properties of your disk on the server, and would auto-tune to make sure that it just runs at the ideal capacity, so it would use as much capacity as it can without ever blocking. So that's the ideal. And here on the side, you can actually see an example of output from this tuning session, and how we find that inflection point of where we want to put like the maximum useful disk concurrency. So if you go and Google for Disk Explorer, this is a tool that's been written by Avi Kiviti, our CTO, that basically does this and also generates those nice graphs for you. So remember that I've said that each shard is completely individual, but the problem is that the disk is still a shared resource for the entire machine. So how do we take n individual I/O schedulers that basically manage one shared resource? They're going to step on each other's toes, and that's going to become a problem. So in order to solve that problem, we have a very nice mechanism of coordinating between those individual schedulers. And this mechanism is not only allowing them to manage the disk together, it also allows them to do so in a way that's NUMA friendly. So what's the idea? Each I/O scheduler that runs on a separate shard basically grabs the list from a shared pool, and then you only have to synchronize that momentary access to the pool, where you pull up your list and you use whatever you can, and whatever spare capacity that you have, you put back in the pool. And then most of the work is being done on individual shards without locking, and only when you take the lists or you put them back, then you have to synchronize for a very, very short amount of time. And the rest of the time, you're like doing work completely independently and in a way that's NUMA friendly. And the reason why we don't have a static division of capacity between the shards is because the disk is a shared resource, and also a potential bottleneck, because we are actually able to saturate the disk even on fast disks, which is something that a lot of other databases cannot do. So it's very important that we actually put back into pool whatever spare capacity we have. Remember, the access patterns between the shards might not be balanced because of data sharding, basically. So it's very important to have this kind of low cost coordination between the shards. So in conclusion, we've seen that the hardware has changed significantly in the last 20 years. And a lot of our assumptions about how stuff behaves in terms of relative speeds have been violated, and we need to rethink a lot of the design of our software. In a sense, software, both in terms of the kernel and user space programs, is now the new bottleneck of our architecture. And in order to solve that, we need to rethink the way we write software and think about physical servers, even like single machines, as distributed systems, and we need to apply distributed architectures even on single servers. So just to give you an idea of how this translates into real world performance. So this is results from actual clients that are running Scylla in the field. So for example, Comcast has replaced a cluster of almost 1,000 Cassandra nodes with 78 Scylla nodes. Those Scylla nodes are actually larger than the original Cassandra nodes, but not by so much. But this was possible because you can actually run Scylla on large nodes, whereas Cassandra couldn't scale to a large number of cores, so you couldn't even run it on larger machines. So not only is performance better, you can actually utilize larger and larger machines, and you can do both horizontal and vertical scaling. And in terms of latency, this is also from one of our clients. You can actually see in the graphs, this is a graph of P99, so 99th percentile latency. And you can see that the Scylla latency is much better than Cassandra. So it's a drop from like 200 something milliseconds to about 25 milliseconds latency. And it's like stable, okay? So it doesn't fluctuate a lot. And this is like the P99, so the average is even a lot better than this. So you can actually see how this architecture is much better in the real world. And one of the most frequent questions that we get from people is that it's still so much faster than Cassandra because it's written in C++ instead of Java. And the answer is like, not really. Okay, the answer, Scylla is much faster than Cassandra because of its unique architecture. The reason it's written in C++ is because it's impossible to implement this architecture in Java. So this is basically what's in C++. So thank you very much. And if you have any questions, now is a good time to write them if you haven't already. And let's check the chat to see what people have been asking.
Thank you, Avishai. Now it's time to hear from you, our audience. If you have any questions for Avishai, please again use the Q&A button located at the bottom of your screen to ask your questions. Also, if you have any private questions that you'd like to ask, please use the Contact Us form on our website at ScyllaDB.com. We've already had some questions asked during the presentation, so let's see what we've already got queued up. First question is, how does ScyllaDB work when we have data that creates a partition every 5 minutes, and after 5 minutes deletes a few records from the first partition based on success or failure, and then writes them with a +1 retry count?
So the answer is that you want to have a lot of concurrent partitions active. Okay, so if you only have one partition active at any given time, you're going to have horrible performance because then you're not going to be able to utilize multiple shards and multiple nodes. So you want to break down your data access patterns to use a lot of partitions. And it's okay to have partitions that rotate like every few minutes. This is basically how you do a lot of the time series data sets that people are running on Scylla. But you still want to have at any given time a lot of partitions active. And I'm talking like thousands or tens of thousands of partitions active, if not more. Okay. And in terms of deletion, it's not a problem. Okay, so Scylla deals with deletions using something called compactions, which I'm not going to talk about too much, but you can read about it after. And this is like part of the normal operation of the database, and it's just fine, just the way it's designed to do.
Okay, the next question was, how does hyperthreading the cores help or hurt or have no effect on performance?
Oh, so that's an excellent question. So basically, hyperthreading is a trick that that's being done in CPUs for a very long time now to go around the problem of CPUs stalling on access to memory. And the idea is that if you have computation running and suddenly you need to wait for memory, then you can run a different hyperthread during that time. It's somewhat similar to what kernels are doing when they switch between threads. It's just done the hardware. So you would have two sets of registers basically, and when you're waiting for memory, then you switch from one set of register to the other set of register, and you run that computation. So it's not exactly the same as having two cores, because if one thread is not memory intensive, meaning it's running some kind of tight loop and doesn't need to stall, then you're not going to have time to run the other hyperthread. So you're not going to see like 200% speed up. And in terms of Scylla, we still use memory, of course, and we use it extensively. So we are able to capitalize on hyperthreads. So probably you don't want to disable them. And also in most of the cloud servers, you can't. But it's not the same as having multiple calls. You probably want to have as many calls as you can have.
Okay, let's see. The next question we have is, what happens when we scale a machine from 16 cores to 32 cores? Does it dynamically shard?
So yes, basically when Scylla runs, it checks dynamically. Every time it runs, it checks the number of cores that you have, and it's going to shard the system based on the number of cores that you have. The only problem with this is distributed data, because each shard owns like different data set. So you might need to do something called rebalance, and that is a process that might take some time. Basically, moves data between shards. But moving data between shards is much cheaper than moving them between nodes. So if you're adding or removing nodes, you're also going to need to rebalance. But rebalancing between nodes is going to cost you more. So that's basically the answer. In practice, not a lot of people change the size of machines. So it's not really a problem. And if you plan to do this a lot, then you might just want to add more machines, especially if you're talking about virtual servers. But yeah, you can do that. It's not a problem.
Great. I think we also have a new feature called load and stream in Scylla 4.5 that also helps when you're migrating to bigger boxes, right?
Yeah. It basically speeds up the rebalancing and bootstrapping of new nodes. So.
Okay, next question here. Can CPU-bound Scylla processes map to individual disks on a host?
So the short answer is no. Basically, Scylla is designed to utilize like one large storage pool, and the rationale behind this is that even if you have individual disks, the disk controller is still shared. So you're going to be blocked on a shared resource anyway, and you're going to manage it anyway. So it doesn't make a lot of sense to treat individual disks as individual, especially if you're running on virtual servers. So that's like the short answer.
Okay, let's see. Seems like the next step for you is, this is more of a comment than a question. Seems like the next step for you is to optimize IOs to use the raw devices instead of using a file system like Oracle ASM.
Yeah, so we did talk about it, by the way, and I've had a conversation with our CTO like a year ago about this. And there's like, we can maybe get a little bit more performance from it, but right now XFS is good enough. And there are other improvements that we can do that will probably give us like more of a boost. So maybe we could squeeze a few percents out of it, but right now it's not worth it. It's like fast enough, and there's like other gains to be had in other places.
Okay, how does running other software on the same server as Scylla, as an example, Zabbix or other agents, how does that affect performance?
Ooh, so that's a very good question. So because Scylla is basically, it uses Seastar as a mini operating system in user space, the resources that Scylla consumes are basically like, you want to give it total access and total control over the resources that it has. So if you're running a Scylla instance and you look at like normal monitoring, you're going to see that it consumes 100% of the CPU no matter what the load is. And you don't actually know what the load in Scylla is until you look at the Scylla metrics, because Seastar is going to manage the CPU by itself. So it's going to consume all the resources. First time when you boot Scylla, it's going to allocate all the memory on the server. It's going to consume all the CPU. It's going to take all your disk. because it's basically an operating system that's going to manage those resources in itself. So you don't want to share the server between Scylla and other software. What we do when we have management software like monitoring, stuff like that, is we tell Scylla, let's say the server has 16 cores, run on 14 cores and leave 2 cores on the side for other tasks like managerial tasks and stuff like that. But as a thumb rule, don't run Scylla on the shared environment unless you're talking about like Kubernetes and stuff like that.
Okay, the next question I have, this I'm going to, because I just looked up the links for this, so I'm going to answer it. You mentioned Red Panda and Value Store as other Seastar using projects. Where is Value Store? I can't find it. So I'm going to share out 2 links for you guys here in the chat. The first one is a blog on Value Store, a memcached alternative built on Scylla. And the second one is the GitHub project, which is from a company, Sensiphone /Value Store, VALUSTOR. No E's on value or store. So I just wanted to share those links with you then. And now this is the next question. What happens if workloads on different shards are highly skewed? How do you mitigate this problem?
So this is not necessarily a problem for shards per se, it's a problem for any partitioned architecture. So in distributed systems, whenever you partition data, you might have some kind of imbalance of either data distribution, like you might have, like, let's say 90% of data on a single partition, or imbalance in the access patterns, meaning the workload. So like 90% of the throughput is on a single partition, for example, and that's a problem. The way you deal with this is you break down in your data model, you break the data down into more and more partitions. So you change the partition key, basically. So let's say that your data is keyed on, let's say, client ID, and you have one big client and like the rest of the clients are small, then you would introduce a secondary layer of partitioning, say client ID and the individual user ID or the individual like document ID or whatever, and then you have more partitions basically. The answer to this kind of question is always more partitions.
Okay, let's see. The next one is on hardware server with 24 NVMe drives. Do you recommend using MD RAID, or may you have a positive experience with ZFS?
So Scylla is designed to run on Linux and Linux only. And Linux doesn't have official support for ZFS. Yes, some vendors do provide ZFS for Linux, but we don't support it. The recommended configuration for Scylla is using RAID over, and like XFS over RAID, and this is what Scylla does automatically for you. It would automatically RAID all the drives on, let's say, EC2 in the machine, and automatically format it to XFS, and this is like the only supported configuration.
Okay, next question. A comment, wonderful session, thanks. Thank you for attending. Thank you to everybody for attending. But here's the next question. What tools are made available for monitoring Scylla if third-party tools are not to be used? So
first of all, I didn't say don't use third-party tools. I said that you can, but if you do, you want to leave like some calls for it. So tell Scylla not to run on all the calls. We do have our own monitoring solution that's called Pseudomonitoring, and it integrates with third-party solutions. So what we recommend is that you use Pseudomonitoring, and then it can export the data from Pseudomonitoring to Prometheus or Datadog or whatever it is that you use, and you're going to see the data like with the rest of your data on your favorite monitoring system, and like you don't need to do almost anything, and it already takes care of collecting all the relevant metrics for you. So it's very easy.
Thanks. Let's see. One other follow-up question from a user. Workload skewness has a stronger impact on ScyllaDB because some of the cores may be idling in some of the servers. Any comment?
So it's like yes and no. Yes, you're going to have this problem of distribution between calls, and which you might not have on, let's say, MySQL, because MySQL might be able to use like the calls for like any data that's on the server, and that's true. But it's not really a problem in practice, because if you're using Scylla, then you're going to have partitioning anyway, because it's a distributed system. Okay, there's no reason to use Scylla if you don't have some kind of partitioning scheme in place anyway. So if you're going to have data that doesn't partition well, don't use a distributed database. That's the only answer I can give you. Like, it has nothing to do with Scylla.
Okay, I'm also going to share out the link to how to integrate Scylla with Datadog, a tale about Datadog and Prometheus integration. And that's the questions we have for today. I wanted to thank everyone again for attending. In due time, you will find this presentation available on the ScyllaDB.com homepage in our webinar section for on-demand viewing. Also remember to register for p99conf.io. Plus, you can register for our next virtual workshop on July 23rd. For now, on behalf of Avishai, myself, and all of us at ScyllaDB, enjoy the rest of your day.